Hello students, I hope everyone is fine. I hope you are staying safe. Remember to sanitize. Remember to put on your masks always, avoid unnecessary movements. Please visit whenever it is a must. Try to stay home and then remember always to sanitize. This is Teacher Bernard from Trinity College in Abengo, and I came here to teach you Senior 5 Chemistry, Deviations from Raoult's Law. Before we broke off, we had looked at ideal solutions, and we explained what ideal solutions are. But the purpose of this topic is to look at real solutions. Those are the solutions that deviate from Raoult's Law on an ideal solutions. Why do some solutions deviate from Raoult's Law or from ideal behavior? Some miscible liquids, on mixing them, strong intermolecular forces of attraction are formed between their molecules. These strong intermolecular forces of attraction formed between the molecules lower the escaping tendency. In other words, the escaping tendency of the molecules in the solution formed reduces lower than in the pure components for the miscible liquids, maybe A or B. So, due to the reduced escaping tendency, the vapor pressure of the solution is lower than what Raoult's law predicts. And because these molecules form stronger intermolecular forces of attraction between them, there is a contraction in the volume on mixing the two miscible liquids. In other words, the total volume expected, the total volume of the solution formed is lower than the total expected volume. Again, due to strong intermolecular forces of attraction formed between the molecules, the formation of this mixture, the formation of these solutions is spontaneous or it is exothermic. Heat is given out, or the enthalpy change for the formation of the solution is negative. On the other side, some miscible liquids, on mixing them, there is some kind of repulsion between the molecules of these two miscible liquids, or weak intermolecular forces of attraction are formed between the molecules of these two miscible liquids. Due to weak intermolecular forces of attraction formed between the molecules of the liquids in the solution, there is a higher escaping tendency of the molecules to the vapor phase, and therefore the vapor pressure of the resultant solution is higher than what Raoult's law predicts. And again, due to the tendency of the molecules in the solution to repel each other, you find that there is some expansion of the solution. The total volume of the solution is higher than the expected total volume. If you mixed 40 of maybe liquid P and then 40 of liquid Q, if they form a solution with a positive deviation, you find that the total volume is not 80, but around 85 or 87, something like that. So again, another characteristic we need to know is that if, due to repulsion again between the molecules in the solution, you find that it is not easy to form these solutions. Their formation is not spontaneous because they tend to repel each other in the solution. And therefore, you must invest heat. The enthalpy change for the formation of the solution is endothermic, or it is positive, or heat is required to form these solutions or mixtures. That one we have just explained is what we call the positive deviation, and of course the first one was the negative deviation. So if we are to concentrate specifically on the negative deviation, why it arises, I've already explained that, and you should right now be able to answer this question. Explain why some solutions deviate negatively from Raoult's law, and then state any three characteristics of solutions that show negative deviation from Raoult's law. Explain what causes these characteristics. We have already looked at these characteristics and you should be able to summarize them. The vapor pressure of the solution is lower than what Raoult's law predicts. And then you should, what's the explanation of that? The explanation is behind the intermolecular forces of attraction between the molecules in the solution, between the molecules of the different components in the solution being strong, lowering the escaping tendency. And if the escaping tendency has lowered, it means that the vapor pressure is going to be lower than what Raoult's law predicts. And then so that's the first characteristic. The vapor pressure of the solution is lower than what Raoult's law predicts. And then the other characteristic is that there is a contraction in volume. There is a contraction in volume on formation of these solutions, or the change in volume, the volume change is negative. Or someone can say the expected volume is lower than, the total volume of the solution formed is lower than the expected volume. And then someone can also say the third explanation is that heat is given out. The third characteristic is that heat is given out on forming these solutions with negative deviation. So you should be able to explain those three. And then examples of miscible liquids that form mixtures with negative deviation from, so they include water and sulfuric acid. Adding water to sulfuric acid or sulfuric acid to water, heat is given out and there is a contraction in volume. We have ever performed that experiment. Water to nitric acid also, it is the same story. Water and hydrochloric acid, it is the same story. Aniline and aminobenzene, aniline and pyridine. Aniline is the same as aminobenzene. So mixing these two also, they form a negative deviation, a solution with a negative deviation. And then here I have a question for you. Explain why a solution of sulfuric acid in water deviates negatively from Raoult's law. The reason is behind the very strong intermolecular forces of attraction formed in the solution of water and sulfuric acid between the molecules of water and sulfuric acid. And these intermolecular forces of attraction are stronger than those in pure water and then those in pure sulfuric acid. And if we are to go into deep explanation, actually it is because sulfuric acid ionizes in water. So the formation of hydroxonium ions that are positively charged and the sulfate ions, that strong intermolecular force of attraction between the positive and negative is stronger than the hydrogen bonding in pure water and then pure sulfuric acid. But the main thing is talking about strong intermolecular forces of attraction formed in the solution of sulfuric acid and water that causes the escaping tendency to lower, and then everything else that you need to talk about a solution with the negative deviation. Vapor pressure composition diagram for solutions with negative deviation. It is always important to now to draw it and then the explanation. We are going to consider two miscible liquids P and Q, whereby P is more volatile than Q. That means that liquid P has a higher vapor pressure than Q because P is more volatile than Q. Now, since P and Q form a solution that deviates negatively from Raoult's law, it means that the vapor pressure composition curve for the solution of P and Q will always be below the line for the ideal solution. In other words, if the solution was ideal, it would follow that line you see dotted there. But since it is deviating negatively from Raoult's law, it means that due to the explanation I've already given you, the vapor pressure of the solution will always be lower than what Raoult's law predicts. But then what is important is to know that the intermolecular forces of attraction between the molecules of P and Q, they increase but not indefinitely. They increase up to a maximum point, A. At point A, we have very strong intermolecular forces of attraction between the molecules of P and Q. And the escaping tendency at that moment is very low. In other words, it is the lowest or at a minimum point. And the vapor pressure is also at a minimum point. And due to very strong intermolecular forces of attraction, the liquid mixture at point A with the composition Ca behaves as if it is a pure liquid of its own. And that one we call it an azeotropic mixture. We shall look at azeotropic mixtures in the next video. PA is the vapor pressure of the azeotropic mixture. Ca is the composition of the azeotropic mixture. You should be able to explain the shape of that curve. Normally they ask how to explain the shape of that curve. Adding Q to P, I want you to note that the vapor pressure of the solution goes on decreasing until a minimum point and then increases again up to point P, not Q. But why is that so? It's because adding Q onto P, stronger intermolecular forces of attraction are formed between the molecules of P and Q. And that one lowers the escaping tendency. And since the escaping tendency goes on lowering, you know what will happen is that the vapor pressure of the solution will go on lowering below what Raoult's law predicts until a minimum point A where we have the strongest intermolecular forces of attraction. I've already talked about that. And if you want to explain, you should be able to explain something related to this. Explain the shape of the graph above. You should be concise and precise, just straight to the point, and then should explain something related to that. Just something similar to the explanation for negative deviation. Okay, so we continue. Now, if we are to draw the boiling point composition diagram for solutions with negative deviation, then we have to remember that boiling point is inversely proportional to what? To vapor pressure of a solution or a liquid. If a liquid has a high vapor pressure, then it means that it has a low boiling point. And if it has a low vapor pressure, and then it means that it has a high boiling point. So since P is having, we are still going to consider two miscible liquids P and Q. Remember, liquid P has a high vapor pressure and liquid Q has a low vapor pressure. That means that P has a low boiling point, but then Q has a high boiling point because Q is less volatile compared to P. The azeotropic mixture, if you look at this vapor pressure diagram, it has the lowest vapor pressure, not so? And remember, we said it behaves as if it is a pure liquid, meaning it has a boiling point of its own. So if you compare the azeotropic mixture formed with the vapor pressure of the two, that is P and Q, the azeotropic mixture has the lowest vapor pressure, and therefore it means that it will have the highest boiling point, Ta. The boiling point of pure Q is TQ. The boiling point of pure P is TP. I want you to note that we have pure P at 100% P. At that point, we have 0% Q. We have pure Q at 100% Q, and then at that point, we have 0% P. Now, you must be able to label the phases present in that diagram, and then you should also be able to label the curves X and Y, which one is for the vapor, which one is for the liquid, and then you should also be able to label the composition of the isotopic mixture Ca. And then another important thing that you normally want is to explain the shape of this curve. Features of the diagram are that, as I've already explained to you. Now, I need you to answer for me this question. Describe the trend of the curve Y from point TP to point Q. The explanation, the description, I think I gave it to you here. Boiling point of the mixture increases with increase in composition of Q up to point A. I want you to note here that they gave for you a specific portion of the curve where they want you to concentrate from point TP to point A. That's where they want you to explain. So, the explanation of the curve is, as you see, basically it is all about on addition of liquid Q to liquid P, strong intermolecular forces of attraction are formed between their molecules. These forces increase in magnitude with increase in the composition of Q. This causes the escaping tendency of the molecules in the mixture to go on reducing, on heating. The vapor pressure of the mixture goes on reducing. And therefore, a higher temperature or more heating is required to raise the vapor pressure of the solution so that it is equal to the external pressure. This causes the boiling point to go on increasing up to the maximum point. That is, at the maximum point, we have the isotopic mixture. This maximum boiling point is the boiling point of the isotopic mixture, whose composition is Ca. That's how you can explain the shape of that curve, and then this is how you can describe it. Now, what is also always important is to know how to describe fractional distillation. We looked at fractional distillation, how we can describe fractional distillation if the solution is ideal. But then, how can we explain fractional distillation if at all we have a solution with negative deviation? We are going to consider the mixture above of P and Q, which has a negative deviation from Raoult's law. And then we are going to use the diagram below to describe what happens if a mixture containing 45% Q is fractionally distilled. I want you to note that 45% Q is closer to P. You must learn how to interpret this diagram. And it is around here at that point you are seeing, just by rough estimate. So if we are to describe the fractional distillation from the diagram, like what happens? They just want you to use the diagram and you explain or describe what will happen if a solution of a given composition is fractionally distilled. The important aspects you must talk about, I wrote for you, I summarized them for you there, are the successive boiling points. What is the starting boiling point of the liquid mixture that we are starting with at 45% of Q? And then what happens to the boiling points of the successive mixtures we get? So you must talk about the successive boiling points of liquid mixtures, and you should show that they are reducing. And then you should talk about when the liquid boils, when the liquid mixture boils, it always gives off an equilibrium vapor. So we are always interested which component is richer, like which component is much more, or that is contained much more in the vapor, in the equilibrium vapor formed. That is the composition of the vapor. And the composition of the vapor is always rich in the more volatile component. So, and then you must talk about what is collected as the distillate and what is collected as the residue. So, for example, here we are going to say a liquid mixture containing 45% Q. When heated, its temperature rises until when it boils at boiling point T1, giving off an equilibrium vapor B, whose composition is at B. If you draw a dotted line down, the composition of that vapor will be B. And it is richer in the more volatile component P. You can see that we are going to the side of P, which is more volatile. And then cooling that vapor at B, we get a liquid C of the same composition as the vapor. And then that liquid C, when it is reheated in the fractionating column, what happens is that it boils at a lower temperature T2, and then giving off an equilibrium vapor D, whose composition is at D. If we draw a dotted line downwards, if this vapor is cooled, again in the fractionating column, remember we said all those things take place in the fractionating column, continued heating and recooling. And then it gives off a liquid E of the same composition as the vapor. And this liquid E, when it is reheated, again in the fractionating column, it boils at a lower boiling point, T3, to give off an equilibrium vapor at F with the composition higher in the more volatile component, P. Then successive cooling and reheating of the vapor leads to formation of pure P as the distillate. Now, the azeotropic mixture, remember, it is behaving as a pure liquid, and therefore it is the one that is going to remain in the distillation flask as the residue and not Q. So we shall have the azeotropic mixture as the residue in the distillation flask, and that's how you're supposed to explain or describe. So using the diagram above, describe what would happen if a mixture containing 20% P is fractionally distilled. After being able to explain for you the one for 45%, please, I request you to explain the one for 20%, and I think that is 80% Q. 20% P is 80% Q. Positive deviation. We have already explained positive deviation and how it arises. It is entirely due to weak intermolecular forces of attraction formed between the molecules of the different components in the solution, and these intermolecular forces of attraction are weaker than those in the pure components. So the escaping tendency is high, the vapor pressure is higher than what Raoult predicts, and since molecules tend to repel each other, there is an increase in volume. And then, since again molecules tend to repel each other, heat is absorbed or heat is required from these solutions. So, if you have been following properly the explanation for negative deviation, it is just the negation or the opposite of negative deviation. The explanation for positive deviation, the diagrams and everything, and therefore you will find that most of the work here in positive deviation is exercise. They are exercises. You're free to consult me using my number. Most of you have my number where you get challenges, but most of these ones are exercises. Examples of solutions that form positive deviation: water and ethanol, propanone and water, propan1-ol and water. And then here I explain why the solution of propanone in water deviates positive from Raoult's law. You should be able to explain that. Basically, it is because propanone molecules, basically associate through Van der Waals forces of attraction. And then water molecules, they associate through hydrogen bonding. So you find that adding propanol to water interferes with the hydrogen bonding in water, creating weak intermolecular forces of attraction between the molecules of water and propanol. And then the escaping tendency of the molecules in the solution are higher in the solution, and just because the intermolecular forces of attraction are weak. And then the vapor pressure is higher than what Raoult predicts, and etc. all the explanations for the positive deviation. So the vapor pressure is that vapor pressure composition diagram. You should be able to explain it in relation now to intermolecular forces of attraction becoming weaker and weaker. The other ones become stronger and stronger. And then you should also be able to label the important parts. Then the boiling point composition diagram, you should be able to label it right now. And our next topic will be azeotropic mixtures. What are they? The methods of separating them, their similarity with pure liquids. And then thanks for being good students, for attending. I remain Teacher Bernard Ssegujja. That's my number. If at all you need to consult something, maybe I've not understood something, that's my WhatsApp number again. Please, you're free to consult using my inbox on WhatsApp, and that's my email. Some of you may be fans of email. For this and more resources, you can visit the link below, and then you get more of this video and then other resources you will need. Thank you very much for attending.